finally make our way into Chapter 6 with 6.1 Law of Sines. What we need to be able to do when we walk away from this video is to be able to recognize the difference between the strategies for right triangles and the strategies for oblique triangles. What are oblique triangles, you might ask? Well, they're not right triangles, and besides that, we're going to get into that more. So objective number 2 is to use the law of sines because, hey, that's what this section is all about. And 3, find all parts of a triangle. 4, model any triangle situation like we have been doing with our pictures. So here's a quick warm-up. Find the height of a building that casts a shadow 30 feet long when the sun is at an angle of elevation of 80 degrees. Here's my long drawn-out website that I got this lovely image from. So what we do know is that we have an angle of elevation, which is 80 degrees. And remember, an angle of elevation is just an angle from a horizontal. So we know that this is a horizontal. We also know that hopefully our building is upright. Okay, and so we have a shadow that is 30 feet long is what they said. So here we can recognize this. Hey, this is a right triangle, and I want to find this side. So this is where we would say right triangle, hey, trig functions. Let's go ahead and use tangent with this reference angle, because tangent is going to link that angle to these particular sides, this opposite and this adjacent side. So I get x over 30. And now to solve for this x, which is what I'm trying to find the height of the building, we would just undo what's being done to it, multiply both sides by 30, and what you would get is x is approximately 170.14 feet. So there we have it. So you may be looking at this picture and starting to think, alright, I'm getting kind of sick of right triangles, because when in life do you necessarily have a perfect landscape that's horizontal? Or what would you do if it wasn't horizontal? So that's where we're going to start addressing these oblique triangles. So we learned in Chapter 4 all about right triangles, and now we're going to start to learn about non-right triangles, and that is the definition of an oblique triangle. So one thing I want you to note is if you were given these two triangles, neither one of these you can say is a right triangle, because none of these angles are labeled as right triangles. So ACTs will do that often. They'll give you a picture that looks tauntingly like a right angle or a right triangle, but it's not unless it has a marking. So now I just created that to be a right triangle. This is a right triangle. This is still an oblique triangle. So here is a big skill to acquire before we head into this and trying to evaluate law of sines. One thing is, whenever you label a triangle, what you'll want to do is use uppercase letters for the angle measurements and lowercase letters that correspond to the opposite side. So what I mean by that is if I drew a triangle like this, then I could label it A, B, C, or whatever. You could even do something like this, A, B, C. But the idea is you got to use corresponding lowercase letters to label the sides opposite of the angles. So this side needs to be labeled very specifically little b, because it's opposite of big B. This side would be C, and this side would be A, because they are the opposite sides to those angles. So same thing over here, we have little a because it's opposite of the big A, little b, and little c. This setup, when you label these correctly, will really help you with the law of sines, otherwise your ratios will get mixed up. Alright, some things that we already know. The interior angles total up to be 180. And now when we're studying these right triangle, or when we're studying these oblique triangles, we cannot use the Pythagorean theorem anymore. Why, you might ask? Well, the Pythagorean theorem was specifically a leg squared plus a leg squared equals a hypotenuse squared. And by definition, a hypotenuse is going to be the side opposite of right angle. So the Pythagorean theorem only works on right triangles. That leaves us in kind of a tricky situation when we're trying to solve these sides of an oblique triangle. We can't, even if you know two of them, you can't use the Pythagorean theorem anymore to say, hey, this squared plus this squared equals this. So you do not have to write this down, but I'm just going to quickly run through this, and if you follow, which I know you all can, pretty much you're a math genius. So we're going to just play around, and we're going to drop down an altitude, which is just a right angle to one of the vertices. So what I did was I created a right angle or a right perpendicular line to this side and then drew it up to this angle C. So do note that I have created two right triangles. Alright, we're going to consider how H is related to the angles A and the angle B. If you did look, what you can see is that H could be set up using a trig functions like this. Because if you look at angle A, let's use that H as the opposite side, and then this B would be the hypotenuse, because this is a right triangle, so we would have sine of A is equal to opposite over hypotenuse. There's that right there. And then sine of B would be H over A, because that also is going to be the opposite and the hypotenuse of that other right triangle. We're going to solve for H now. So if you wanted to, you could multiply B to both sides. Alright, those cancel out. Multiply A to both sides here. Those cancel out, and what you get is this. So now what we just found out is that H is equal to this, and H is equal to this. So what we're going to go ahead and do is we're going to set them equal to each other, because this right here is that, this right here is that, and they must be equal since they're both equal to H. Alright, and then what we can go ahead and do is divide this side by AB, but whatever you do to one side, you gotta divide by the other. What you'll notice is these cancel out, oops, sorry, this cancels out, so we still have an A over here, and what we get is part of our law of sines. So there is the proof. Understand, behind everything that we do, there is proofs that will explain and have reason for why things exist. So we could also drop an altitude down like that on our triangle, and what we get is our law of sines. So here is our law of sines. I would box that in your paper, put some stars by it, maybe a few hearts, because that is what's going to carry us through this section. And all that's saying is you can take the sine of an angle and then put it over its opposite side, and that equals the sine of any other angle over its opposite side. So sine of another angle over its opposite side. There are three angles, three sides on a triangle. You can set up these proportions. Here are the steps that we're going to be using to solve these problems, and I will do an example of this using these steps exactly. The hardest thing about this is to be aware of SSA or ASS, and what we are going to be doing is skipping over any problems that you come across in your homework that have an ASS or SSA pattern. And I'm going to go into a little bit more about how to identify that, but if you can remember back to geometry, what we do is we look at the connection of sides and angles, and then we create this name for it. Alright, so example number 1, we're going to just have a problem like this where they give us an A, a B, and a little a. Alright, so find unknown values. Step 1, draw a diagram. So I drew a diagram like this. Keep in mind that it could have been different. Alright, you could have drawn something like this, A, B, C, then your labels are just going to be slightly different. That's a C. And then A and B, and then so you would just have to label properly that you know this side, this angle, and this side. Okay, so it looks slightly different, but we're going to get the same results. So step 2, list all. So that's where you're going to just do this column of all the angles, do the column of all the sides, and then you're going to list out what you know. And this, having an angle with its opposite side, gives you a full fraction or a full ratio. That's exactly what we want when we're doing these law of sines. Okay, because we're going to use that full ratio to help us solve these proportions. One other thing, step 3, is be aware of SSA. So I'm going to go into this a little bit more. But what you want to do is you want to start with one of your pieces, and you want to say, okay, here's an angle. You want to skip no more than 2 parts. So I don't want to go this direction, because otherwise I'm going to be skipping over this in order to get to my next known. And if that's the case, well, basically you don't want to skip over 2 pieces. So we're not going to go this direction, okay? We're going to go this direction and observe that, okay, I did have to skip over 1 part. That's okay as long as it's not 2. So what we had was a known angle, another known angle, and a known side. We have AAS. Okay. Okay, so step 4, use the law of sines. So being that we have that full ratio, what we're going to do is we're going to take the sine of big A over little a, and that's this right here. We took sine of 45 over that little a, which was 30. That was known to us, and now what we can do is solve a proportion for b. So cross multiplied, a lot like we did for the conversion between degrees and radians. We knew that the cross multiples were equal to each other. So b times sine of 45 was equal to 30 times sine of 50. Right? So then we can go ahead and solve for our b by dividing both sides by the sine of 45 and the sine of 45. One thing that I please don't want to see is people dividing by sine and sine. Sine itself is not a number. Sine is an operation. It would be like saying plus divided by plus. Right? Sine has to be with an angle. So do note that this whole sine of 50 is just a side-to-side ratio. It's just a number. And this whole thing is what we're dividing. So when you type this into your calculator, you're going to type exactly that. When you do that, you're going to get approximately 32.5. Which leads me to mention one of those starred things on the previous slide. On the previous slide, what I said is don't forget that we can always calculate another angle. If you know 2, you can just take them both from 180 and you got your last angle, your third angle. And then the other thing is we're going to continue to use this ratio because the idea is we don't want to use this 32.5 since we rounded, and that could kind of skew our answer. So we're going to try to use as exact answers as possible. So we'll repeat this process. Remember to avoid, yep, I already just said that. And then now what we're going to have is that sine of 45 again, or sine of big A over little a, is equal to sine of this 85 over that little c. Try that on your own. Make sure that you can calculate it. Pause me because I'm about to reveal the answer. And there it is. So it's approximately 42.3. Alright, how to tell if it's that side angle side, side angle, angle side angle. Do note that these are what we call an included angle. It means that it's connected to both of the pieces around it, so to both of the sides around it. So if you look at, for example, this is what we would call an angle, side angle. You can check that and say, hey, I know the side and it's touching both of these angles, so it's what we would call an included side. Again, you wouldn't want to go this way if I said, hey, here's my angle. You wouldn't want to skip over this unknown, skip over this, skip over this, skip over this, and call this an angle side. Because again, you skipped over too many. You should no more skip over 2. What if I were to take this out, okay, and I would just say that I knew my A. So let's say that this was like 4 or something. The idea is, if you did have that situation, again, this is technically your included side because it's touching this side and it's touching this angle. So it's going to be an angle, side, side. Ooh, that's bad. And truly, it is bad in multiple ways. And again, in your homework, in step 3, it says be aware of ASS or SSA. And the reason why is there's a huge process involved with solving a triangle that's ASS. So it's actually a huge pain in the butt. We're going to just skip those problems. So if you get to step 3 and you check for ASS, you can just skip that problem. You don't have to do it. Alright, we're going to do number 1 from your homework. So first of all, I didn't have to do this because it's in your book. And then now I'm going to go ahead and do step 2, which is going to do my column of angles, my column of sides. Okay, and now I'm going to check myself to see, do I have SSA? And I hope I do, because then I can just skip it for now. But unfortunately, we have angle, angle, side. So I have an angle side. I do have to follow through with this. So I've checked that. I've done that. Oh, I do want to list out everything that I know. So I do know that this is 30 degrees. I do know that big B is 45 degrees. And then I do know my little a is 20. And what I could technically go ahead and do is this is 105 degrees. Alright, so this full ratio is what I want to use. So this is where I'm going to start using my law of sines, that an angle, the sine of an angle, is equal to, over its opposite side is equal to sine of, in this case we're going to say go for B, You don't have to go for B, but I'm going to. And this is where we're going to be able to fill these in. So we have sine of 30 degrees over, and then 20. That was this right here. Equals, and then sine of 45 degrees all over my unknown. So when I solve for this, I will go ahead and set up that the cross multiples have to be equal. So here we go. And then I'm going to go ahead and divide. Cross multiply and divide. When we do this on our calculator then, I get approximately 28.28. Okay, and again I'm going to say don't use this. We're going to want to use sine of A again. So we're just going to use that sine of 30 degrees over that 20 is equal to sine of 45. 105. 105 over C. And when you do that, you're going to get approximately 38.64. So one thing I want to mention is we did not use the Pythagorean theorem because, again, we couldn't. This wasn't a right triangle. We can't use the Pythagorean theorem. So we did have to use the law of sine twice to get us all the pieces we were missing. The other thing I want you to note is that this is our largest side and it's opposite of our largest angle. This was our middle side and it was opposite of its middle side length. And then this was the smallest side length, it was opposite of its smallest angle. You should always be able to look back and check your work in that way. So when you look at this set of practice problems, again, you want to be cautious of that step 3, that if you ever have an angle side, for this night you are going to be skipping those problems. So you don't have to do any work with it, you can just stop. We'll go back and revisit those.